Tree diagrams are great when the number of decisions are very little. We only have a couple of decisions to make, and each decision only have a limited number of options. There's not very many. Otherwise, it gets very large or very difficult to try and show this out. For example, imagine, would you want to list all of the ways or try to make a tree diagram showing every way that you could select a 5-digit PIN number? This would be horrible because the first digit of the PIN number, that would be your first option, the first decision to make. And you would have to choose between 10 different options, the numbers 0 through 9. And then you'd branch off for those. And then you'd go to the second digit of that PIN number. That would as well have 10 different options to choose from. So all of those 10 that you previously had now have 10 branches coming off of them. This would continue for the next 3 digits of that PIN number. You wouldn't even be able to fit that on a whiteboard in a classroom, and that would take you forever to try to write out all of those different outcomes that you could get for this 5-digit PIN number. So we need an easier way to figure out how many outcomes we have in an experiment, because we need these for our probabilities. So let's take a look at the experiments that we did in the last 2 videos. We had rolling 2 die, and to get our number of outcomes, well, our first die, the red one, that had 6 different outcomes. The second die, the green one, that as well had 6 different outcomes. And we know that when we rolled the 2 dice, we had 36 different outcomes that we saw in our table. Well, 6 times 6 is equal to 36. Let's also take a look at our lunch menu experiment that we had in the last video. The first main dish, we had 3 different choices to choose from: the hot dog, burger, or pizza. The drink also had 3 different options. We had to choose between milk, soda, or water. And then lastly, the dessert had 2 options. And we also saw that our total number of N branches for the lunch experiment had 18 different N branches. So that told us that there was 18 different outcomes in that experiment. Well, 18 is the same thing as 3 times 3 times 2. So let's take a look at the pattern that we have here. This is essentially our fundamental counting principle that says the number of outcomes for each individual stage can simply just be multiplied together to get the total number of outcomes for the experiment. So now let's apply this on a couple of examples here. The first one we have, suppose you take a 6-question true-false quiz, and we want to know how many ways could you answer this quiz. So you go to the first question on the quiz. How many options do you have for that first question? Well, you could choose between either true or false. So you have 2 different options for that first question. We then move on to the second question of that quiz. That question is still true or false, so that one has 2 different options as well. And same for all of the rest of the questions in this quiz. They all have 2 different outcomes. So now, our fundamental counting principle tells us that we can take these outcomes for each individual stage, each individual question, and multiply them together. So that gives us 2 times 2 times 2 times 2 times 2 times 2, which is 2 to the 6th power, which then we can just calculate that, and we get 64. The next one, we have that you're a member of the drama club, and the club has 20 members. How many ways could you select a president, a vice president, and a treasurer for this club? Well, let's suppose first they're voting for who is going to be president. How many people could they choose from to be president? Well, they have 20 different people in the club that could fill that role. But now, most schools don't want the same person to be all 3 of these roles. It wouldn't really make sense for one person to be both president and vice president. They have different names for a reason. It wouldn't make sense for them to fill one person to fill the same role. So, what we need to take into consideration here is now someone out of those 20 would have been chosen to be president. So now when they are going to pick the vice president, whoever that one person was, it's no longer an option. So in our second stage part of this, the vice president, we have one less person to choose from. So we're down to 19. And now we're going to suppose they picked someone for that vice president. Whoever it was isn't an option anymore. So the treasurer only has 18 people to choose from. And now our counting principle says we just multiply these together. So 20 times 19 times 18, and that gives us 6,840 different ways they could select these 3 roles from the 20 people in their group. So now a little bit of terminology here. Our experiments can be performed with or without replacement. Our problem with the true-false quiz, that is with replacement, because what they chose on the first question is not affecting the outcomes on the other questions of the quiz. It's not changing at all. Without replacement is our example with the drama club. They pick someone for the president, and that person is taken out of the mix of possible options for vice president and treasurer. They're not being put back in. So that's where the without replacement idea comes from. The without replacement is a lot of times seen in deck of cards examples that we'll do later on throughout this chapter. So we have one last example here to work through with license plates. So first off, we have our Wisconsin license plates. They used to be made up by this formula here of 3 numbers followed by 3 letters in this. And I first want to take a look at ones where the numbers and letters can be repeated. And I want to know what is the total possible number of license plates, Wisconsin license plates, following this pattern. So that means I have essentially 6 positions in this license plate. I have my 3 numbers and then my 3 letters. So if I first look at my first number of this license plate, I need a single digit number. So my possibilities for that are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And now let's count up how many of those we have from 0 through 9. Well, there's 10 different numbers there. So I have 10 different numbers to choose from for that first position. The second position of the license plate, well, if the numbers and letters can be repeated, this one as well has 10 different options to choose from. And then same with the third number. So now let's move on to the letters. In the English alphabet, we have 26 different letters. So that first letter has 26 options. And same with the second and third because they can be repeated. So now we can take all of these and multiply them together. And when we do that, we get a very large number here. 17,576,000 different license plates that could be made if the numbers and letters can be repeated. The next one, I want to do the same thing, but now my setup is that the numbers and letters cannot be repeated. So that first number, well, we're starting off, they have 10 different options, 0 through 9. But now we're saying that they can't be repeated. So if I'm looking at my options from up above, 0 through 9, let's suppose maybe they use 9. That one's gone. It's no longer an option for the rest of the numbers. So that means I have one less possible outcome for my second number. So the second number only has 9 options to choose from. And now they went through and they picked that second number. They used up one of those options. One of them can no longer be in the mix for the third number. Maybe it was 8. It doesn't really matter which one it is. I just need to cross one of the options off. So now if I count up the amount that I have left for my third number, well, we only have 8 to choose from. And now let's move on to my letters. The first letter, there is 26 different options, but then they used one of those letters for that first one. So one of those 26 is gone, which means the second letter only has 25. And now for that second letter, they used one of those 25. So the third letter only has 24. And now we can multiply all of these together to get our total number of license plates. So now this gives us 11,232,000 different license plates when the numbers and letters cannot be repeated.